Hello, my name is Niall Roach, and I am from Lab Section MO2. And for this experiment, I decided to focus on Felix Baumgartner's free fall from space. So I decided I'm going to try and compare the speed of sound with his speed at the time he reaches the troposphere to see if he broke the speed of sound by this point in his fall. I also decided to compare the estimations of speed calculated using kinematic equations with an estimate created by code that uses the momentum principle. And so the main result was that I was able to determine that he did break the speed of sound by the time he reached the troposphere, and that both methods of calculating the velocity produce the same answer. So the first kinematic equation I used was that the final height is equal to the initial height plus the initial velocity times the time plus 1/2 times the acceleration due to gravity times the time squared. But since he's just dropping from the capsule he was in, the initial velocity is 0. So this means that the new equation is the final height equals the initial height plus 1/2 times the acceleration due to gravity times the time squared. So I solved this equation for t, as you can see here, and then I plugged in my conditions, which I've set over here. And so that means the time is roughly 77 seconds. It's actually 76.991, so I just tried to round up to an even 77. So now the next equation I used was that the final velocity is equal to the initial velocity plus the acceleration due to gravity times the time. So once again, the initial velocity is 0 meters per second. So the approximation for the final velocity is negative 9.81 meters per second squared times 77 seconds. And that gives you a final velocity of a negative 754.6 meters per second. And this is negative because I decided to set my axis so that he's falling in the negative direction. So now let me show you my code. Uh, my code, I have his mass, which I looked up the mass, and his mass is 118 kilograms. This is him with the entire suit on. It says initial velocity is 0, and here's the acceleration due to gravity, negative 9.8. I think I'd have it negative 9.81 and thing, but it's still pretty much the same. I have my time, and so I have that the force of due to gravity is the acceleration due to gravity times his mass, and that the net force on him at this time is just the force of gravity. I'm excluding drag at this time because he's not reached the troposphere yet, and that's where so 99% of the atmosphere is below him, so he hasn't really got any force of drag yet. So I have his final velocity is being equal to the initial velocity, or in this case, because it's continually updating throughout the loop. So the velocity is equal to the velocity plus the net force divided by his mass times delta t. So this is just for his position. So it's calculated this, and I run it, and so here I printed. It was run over 77 seconds, and his final velocity is negative. Of course, it's 0 in for the x direction and z direction, so it's negative 754.6 meters per second, and that is equivalent to what I have calculated in my kinematic equation. So the calculations are the same. So thanks for listening.